Okay, got it. All right, thank you. So this is the third of my lectures. It's Engineer's Perspective on the Human Condition. This is the evolution of civilization. And again, my template here is or my cover page. The sun is a source of a heat reservoir. Empty space is a cold reservoir, and the Earth system is a dissipative heat engine. It receives highly energetic, low entropy visible light photons, and converts them into low energy, high entropy infrared heat photons. And in the process of doing that, it does work. That work drives wind, grows plants, and runs the human economy at the end of the day. So we did the evolution of the universe. It's the first 9 billion years, 9.3 billion years. Then we talked about the evolution of Earth, or actually the solar system. Next 4.5 billion years, we didn't get quite to the Holocene. We got to the extinction of the dinosaurs. And part 3 is the evolution of civilization. And this carries on the story from the evolution of the dinosaurs, and it's the evolution of civilization, how civilization came to be, and in the end, we have to conclude with the problem that the most important problem is the sixth extinction. It is underway. It has a name called the Holocene extinction. It already has a name, and of course climate change. And I'm probably going to split these two up into 3. I have already done that for my students. So economics, energy, and then solutions, something like that. And so what we talked about when we talked about the evolution of the universe, part 1, we looked back through our telescopes and time and space this way. And now we're looking back basically in rocks and generating history of the Earth and the solar system using asteroids and so forth. And this is just another figure from Axel Kleiden. He wrote a book called Thermodynamic Earth. It's a great book. It's a graduate level textbook, and so it's really difficult. But this just illustrates how the Earth is a heat engine, and we gain energy from solar radiation. We lose energy from terrestrial radiation. And of course, there's geothermal cycling and geothermal energy. This is heat generation down here, and then that propagates up from the core into the surface. There's biotic activity on the surface. Human activity is part of this. So the human economy is very much part of the Earth heat engine, or the Earth system. Energy conversion and entropy production drive life, the universe, and everything. And that is the big lesson. And there's some quotes from Albert Einstein, Arthur Eddington, and so forth, and Rainer Kummel. This is an economics book. Energy conversion, entropy production determine the growth of wealth. So human economy is indeed a heat engine too. And of course, energy and entropy are ignored by neoclassical economists. And that's in part 3. Part 4, we'll talk about that. Why our economic system is completely failing us. I used to be sort of hesitant to say that, but now I know it's a fact, and I have to defend it in the next lecture. So we are emitting carbon dioxide 10 times faster into the atmosphere than the most extreme event during the Phanerozoic, and that was the greatest extinction event of all time. That's the end Permian extinction 252 million years ago. Including other greenhouse gases and accounting for the faint young sun, the sun is gradually getting brighter, so you needed more carbon dioxide in the atmosphere at the time. Our annual emissions have more than a 30 times global warming potential, as they did during this period. And the amount of fossil fuels we are burning took about 1 million years for the Earth to manufacture. That's a million years of sequestered carbon every single year. Obviously, we can ask ourselves, what could possibly go wrong with those numbers? This is the faint young sun. I covered this last time, but the sun is gradually getting brighter. So if you go all the way back in time, you needed a lot more carbon dioxide in the atmosphere to make up for it. And this is shown here. This is the carbon dioxide. You could see it during those early days during the Archean. Carbon dioxide in the atmosphere was between about three and four orders of magnitude, 1,000 and 10,000 times more the number of actual carbon dioxide molecules in the atmosphere. And again, they were needed to make up for the faint young sun. And the reason for these wide bands is, of course, carbon dioxide doesn't follow a nice path like this. There's both organic and inorganic processes that have been pulling carbon dioxide out of the atmosphere. And so it bounces around. And whenever it gets near the bottom, we're in an ice age. And whenever it gets near the top, we're in a hothouse climate. But amazingly, it has stayed within the boundaries that there's liquid water someplace on the planet. So it's been habitable for life. And this is kind of what led to the Gaia hypothesis. And these two events here, when it dropped this low, the Earth practically froze over to the equator. And again, it was because carbon dioxide was pulled out of the atmosphere. So we covered that. This is shown by global warming deniers, including the top, the alpha deniers. They copy it from a paper that said, that quote, concluded, over the long term, there is indeed a correlation between CO2 and paleo temperature as manifest in the atmospheric greenhouse effect. That's the conclusion of a paper that these guys show. They never obviously read the conclusion, and they just claim, see, carbon dioxide was higher in the past, and it didn't cause a runaway climate or anything like that. But when we take into account the faint young sun, we see that the temperatures, the mean, this is a mean temperature. This is over 10 million years. This is an estimate for 10 million years. So even within that million, 10 million years, it bounced around. But you could see it was about the same as it is now. There was colder times and it was warmer times. But it was never warm enough that we were going to cause a runaway climate, even with the relative CO2 levels being very high, or factor 10 higher. And that's because of the faint young sun. So this is hopefully what I want to teach in part 3. The climate is in a bistable state. We are close to tipping the climate into a 5-degree warmer mid-Miocene climate 15 million years ago. We do not know how close we are. Based on some evidence that I'll show, which is not in this talk, but I'm going to go to more recent evidence and show that it may actually be closer than we think. And then this thing, civilization depends on agriculture, and agriculture depends on a stable climate. And so if we destabilize the climate, we destabilize agriculture, we destabilize civilization. We are warming the climate too fast for the biosphere and civilization to adapt. That is literally true. The rate at which it's warming is too fast for these things. So we have to slow it down in any event. An extinction event is underway. It has a name, the Holocene extinction. And the planet is not in peril. It kind of aggravates me every time I read a headline that says, will this battery technology save the planet? Well, of course it's not. The Earth doesn't need saving. We cannot save the Earth if it did. The Earth is not in trouble. We are. And the question is, can this new battery technology save us? This is a timeline. We covered all of this. I think we got to about here, Cretaceous. And this was a major extinction event called the KT extinction. And it was caused by a meteor which landed in Chicxulub, Mexico, and nearly simultaneously volcanism, the Deakin Large Igneous Province. A Large Igneous Province is an organization here that keeps track of all these things. Here's another one that caused the greatest extinction event that I was talking about. And these things cover millions of square kilometers with basalt rock. Okay, now in the last 66 million years, this is the global surface temperature. It was indeed much hotter in the beginning. This is the surface temperature was between 25, maybe even 27 degrees, a little hotter than that. Now it's 13 and a half degrees. It was 13 and a half degrees and we've warmed it since then about a degree and a half. So we're really close to 15 degrees now. So we've already jumped up a little bit. And this just shows where the Chicxulub crater hit. This is what the Earth looked like. And that you can see there's Mexico, the Gulf of Mexico, and here's the Deakin Trap. It's kind of at the opposite side of the Earth, so the Deakin Trap might have been set off by the meteor. This is just I like this picture. Titanoboa was the largest snake ever. He's swallowing a crocodile whole. 42 feet long, 2,500 pounds, lived 58 million years ago. So it's just one of my favorite animals that ever lived. And this display was in the Smithsonian downtown. I don't know where it is now. It travels around the world. Anyway, that's the Middle Eocene. You can see South America and Australia are parting from Antarctica before they were actually connected. And this change, and you can see that there's still a flow of ocean water around approximately the equator. The Mediterranean was wide open, and South America and North America weren't closed. So this is a very different circulation of water. Now, this is another fun thing. This is this year, August 2023. Had the body mass. You could see 187,000 pounds to 750,000 pounds, 66 feet long. So this is estimated to be the largest, double the size of a blue whale. They just discovered it this year, so it's pretty interesting. By the middle Miocene, 14 million years ago, South America has separated from Antarctica. So is Australia. We no longer have a current that flows in the equator, but we do have a circumpolar current around Antarctica, and that keeps Antarctica cold and allowed it to freeze. Another interesting animal, a megalodon, 23 to 3 million years ago. And you can see here's a killer whale. You can see this puppy could solve a killer whale whole. So pretty frightening creature. Anyway, the last glacier maximum 18,000 years ago. So humans were on we may be going back the Homo genus about 2 million years, 2 to 3 million years. Homo habilis and Homo erectus maybe 1.8 million years. Homo erectus was really the star of the show. They discovered fire. They probably developed language. They developed an impressive stone toolkit, and they also had we think had ocean-going craft that they could sail to some place, or maybe they didn't sail. We don't know, but they reached land that they couldn't see beyond the horizon. Pretty impressive human ancestor for us, and that's the beginning of everything, because Homo erectus is the ancestor species for Homo neanderthalensis, Homo denisovans, Homo heidelbergensis, Homo sapiens, and then there's another one that was just discovered, but I don't know what the name is. Anyway, this is the global surface temperature. That 66 million years, and you can see this is really cool because it shows where India and Asia collided. The circumpolar current was formed, the mid-Miocene climate optimum. Antarctic ice sheet formed about 35 million years ago, and the Greenland ice sheet, the northern hemisphere ice sheet, maybe about 5 or 7. And this is the carbon dioxide. So here's the bands show the temperature of the Earth, and and this shows the carbon dioxide levels. So here's the carbon dioxide levels in parts per million, and you can see carbon dioxide was extremely well correlated to temperature. So where the temperature was super hot, that I showed you, that 25 degrees, 10 or 15 degrees above what it is today. This is the carbon dioxide was highest. And even during these warm periods, carbon dioxide was still much higher than today, and it just gradually fell. The mid-Miocene climate optimum, carbon dioxide jumps up, and then here's us today. Well, we're at, I actually put two dots here, and I guess I didn't show the right curve, but this is 480 CO2. We're at 425 now, which between 480 to 425, say it's about here. So you can see we're right here. But if you add in the equivalent, taking into account nitrous oxide and methane, we're at over 500. So we're someplace around here. So the band of where we are in terms of what do you call it? The global warming potential is the same as the mid-Miocene climate optimum, when it was 5 to 8 degrees hotter than it is today. So we're in a bistable situation. The carbon dioxide is hot enough for the planet actually to be 5 to 7 degrees hotter. What's keeping us cool is the ice in Antarctica and Greenland. Now, more biodiversity means more resilience. This is the biodiversity during the Phanerozoic. As it got cooler, biodiversity increased. So actually, life likes a cooler planet. And this contradicts a lot of what global warming deniers say. So what if the planet gets warmer? Life will like it. But no. It really, really prefers a warmer planet. And as the planet got warm, biodiversity increased. This is what I was talking about climate bistability. This is a cartoon, but as we warm the planet by putting carbon dioxide into the atmosphere, right? Say we're here, there's a point C where we'll jump up to this state. And once we hit this state, we're stuck in this state. We'll be 5 or so degrees hotter, and we won't come back until we hit a point F. So it's like a magnet. If you learned with hysteresis, then you might have remembered that in your high school science classes. So the climate is in a bistable state. So this is just more papers that talk about this, and here we are right here. What we want to do is stabilize the Earth, but we can drop down pretty quick into that hot ass climate. The amok carries nutrients around, and it's in danger of slowing down. And again, another view of the bistability of the climate. And this is part of the reason. This is why it's easy for me to understand. If you have solid ice and you warm it, add heat to it, it will warm as a proportion to the amount of heat you add until you start melting it, in which case it stops warming, and the more heat you add just melts ice. It stays at that temperature. All of a sudden it's all melted, and it will start warming again in proportion to the amount of heat you add until it gets to this phase transition where it starts boiling the water away. It stays at 212 degrees Fahrenheit until the water's all boiled away, and then it'll shoot up. The same amount of heat needed to melt ice with no rise in temperature will cause water to rise 80 degrees C or 144 degrees F. So right now, the imbalance between the outgoing infrared energy and the incoming solar energy, it's heating the planet. But a lot of it is going into melting back the ice, the glaciers, subtropical glaciers, Antarctica. Greenland, and also, of course, the sea glaciers in the Arctic and the Antarctic around Greenland and Antarctica. Okay, these are tipping points. These things, unfortunately, these things are probably going to tip by 2050, or if they're not tipping already. Tropical coral reefs are already committed to extinction, about 1.5 degrees, which we have exceeded last year, and 2 degrees is in the bag, so tropical coral reefs are gone. That's underlying the threat of extinction, because tropical coral reefs are about 30% of marine organisms depend on coral reefs. And some of those will find other kind of habitat, but many will disappear. Arctic sea ice may disappear before 2035. Greenland ice sheet may have already passed the tipping point. And West Antarctic ice sheet may also pass an unrecoverable tipping point. These are references. And the Earth's ability to absorb human-caused carbon emissions could be reduced. Right now, it's 57%. So when you say we're putting in 10 million tons of carbon dioxide, or just carbon in the form of carbon dioxide, 57% of that gets reabsorbed. That's not a good thing, because it's causing ocean acidification. But that will be reduced to 42% within decades by this paper by Duffy. Okay, so here's another paper about the Greenland ice sheet, and it just shows again that bifurcation, or that hysteresis. And that CD area is about 420, 425, right? We are there on the boundary. And that's what it'll look like. We'll skip that one. 10,000 years of carbon dioxide. So this is this, and it shoots right up. we're past 420 now. And this is the temperature up to December 2023. And this is, I have to say, this is NASA GIST data, Goddard Institute for Space Studies. And they're a bit cooler than the other. I've always used it, and I download the data, but they're cooler than the others because they only start at 1880, and I use 1880 to 1910. Everybody else uses 1850 to 1900, and it was cooler here. So there's about 1/10 of a degree difference, and so the Berkeley Earth system is 1.54 degrees for the year. Okay, so you add 1/10 of a degree to all these things, and that's the more legitimate level, because, well, 1850 to 1900 is what they are now assuming is the straw man to compare it to. You could see, though, even with the Goddard data, 1.74, 1.6, 1.7, 1.64, so we're already pretty high. I mean, and trying to claim that we can stay under 1.5 degrees, I think is pathetic now. Oceans are warming, so that's another hockey stick. And here's the problem for us, and this is, well, deniers don't understand it, but I think most humans don't get it, and why people aren't panicked. All of civilization occurred during this very smooth, almost uniquely stable, severely flat, because agriculture was possible. Here's more typical of how the Earth system behaves, and you can't do agriculture here. So we were hunter-gatherers, although there's a recent paper I saw just the other day that said, we did get many of our calories from growing food. There's evidence, although agriculture itself doesn't really leave a lot of evidence. And even going all the way back to Homo erectus, there's some are anthropologists who think that they had some forms of agriculture. And if you think about it, all agriculture is, you eat fruit and vegetables, and you have a middens. And if you know what middens are, they're like your waste site. So even a groundhog community has middens, and animal behavior study middens, paleo anthropologists to study middens and so forth, and that's where our stuff collects. And now, so you can imagine if you're eating fruits and vegetables, and you have a middens and it's full of the seeds, and then next year you find that the stuff you really like is growing out of your middens. Well, you can put two and two together. These people weren't stupid, so they probably figured out agriculture. But if you look at the way the climate changed, there's no way you could depend on agriculture, because the climate wasn't stable enough for it. So agriculture, in order to depend on it, especially grains, you needed a stable climate. You needed something that every year is repeatable. It's going to rain at the same time and so forth. And it's going to get warm in March, April, May, and it's going to start you have to harvest before September, October, November, right? Or something like that. You have to have some stability. So we'll go right past that. But human population growth leverage. And so pre-agricultural growth was 0.01% per year. So very slow growing. And we had good stone tools, and we had fire. And maybe for 800,000, maybe a million years. And this is how many gigajoules per year per capita that lifestyle could generate. Post-ag, once we discovered agriculture, we grew by a factor of 10. The amount of energy that could flow into the human economy. So our growth rate increased, and we increased the amount of gigajoules per year per capita. And then when we hit fossil fuels, our growth went up more than an order of magnitude, and the amount of energy that we can flow per capita is significant. So growth is all about energy flow. And in fact, you can get into more detail than even this. If you study history, the only way to study human history is to study it through the lens of the energy flow through the human economy. And that's how we were able to grow, as we evolved better ways of capturing the available energy in our environment. So hunting and gathering is extremely resilient. That's why they could survive when the climate was varying quite a bit, because they can move and they could follow the game and so forth. It's not very efficient. So once you could do agriculture, you get more efficiency and you can grow the population. So this is a brief history of civilization. I'll go through this. This is from Catherine Duffy's paper. I mentioned Duffy's paper in terms of the ability for the Earth to absorb our emissions. It is definitely falling, and these are other tipping points that might not tip. Well, some of them could tip. Well, I mentioned the Greenland ice sheet, the West Antarctic ice sheet. They're going to tip. Arctic sea ice, alpine glaciers, coral reefs. These are all in this category here. There was a paper published in July that the Atlantic meridional overturning circulation. That's the Gulf Stream goes up this way, and that forms a part of what's called the Atlantic meridional overturning circulation, which is part of the thermohaline circulation, which is that ocean conveyor belt, which conveys not just heat, but also nutrients around the planet. That may shut down. If it shuts down, all bets are off. Our climate is going to change drastically, and it's going to be chaotic. Let's see. Okay, we can skip this. This is the one thing I want to say is there is a mistake in the IPCC report, and they were taking into account this paper from Jeremy Shacken, which goes back to 2012, but it was always believed that the temperature difference between the last glacial maximum and today was only about 3.5, maybe 4 degrees. More recently, in fact, in November 2021, Matthew Osman and Jessica Tierney and colleagues revisited the data and reanalyzed it and said, no, that's wrong. It was actually 7 degrees. What this changes is and they haven't factored this in the IPCC report because that came out in 2019, 2020, the last one, AR6. And I'll show they assume that the amount that the Earth would warm if we doubled atmospheric carbon dioxide, what's called equilibrium climate sensitivity, is 3.2 degrees, which is higher than AR5 and 4 and 3. So they're gradually increasing it. But that's because they assume that it only changed this much. Now we know it changed almost twice as much as that. And it's not, and that's why James Hansen just published a paper in December and says, wait a minute, guys, it's 4.8 degrees plus or minus 1.2 degrees. And I'll show that data. It's not yet in the paper here. But by the way, getting back to our story, civilization has never experienced a dramatic climate shift. But the biosphere, of course, obviously has survived many. I mean, all that stuff wasn't a major extinction event when we saw all those jumps. Of course, none of them were as fast as what we're doing today by like an order of magnitude, even though they look steep. But in the meantime, 88 civilizations collapsed in this 4,000 year period. And the reasons were abrupt climate change. And by abrupt, it's nothing like what we're doing today. We're talking very modest, a 1/10 of a degree, 1/2 a degree, but quick. Overshoot and depletion of resources, and this is local or regional, increasing reliance on complexity, diminishing returns of technology, and read that again if you think technology is going to save us, diminishing returns of technology, inequality, and if you can't solve this, you're not going to solve climate change. This has to be solved, and establishment of an oligarchy, which we have now in the United States, in the world. I mean, we know that, we recognize Russia's, but we don't recognize that we're driven by an oligarchy too. All these stresses are in play currently, every single one of them. This is from the Kemp's paper, just a flow chart of what happens. I'll skip this. It's, well, we're in trouble. This is important. This came out this year, I think in July. These are 9 planetary boundaries. We've surpassed. We're in the red in 6 out of 9, and deep purple in a bunch of them. And we have to solve also. We just can't address climate change, which also, by the way, is in the purple here. We have to solve all of these things if we're going to survive as a species. You can't just say, oh, well, it's only about climate change, and all we need is a carbon tax. The carbon tax doesn't do anything about any of this other stuff. It won't even solve this. I mean, I'm thinking to myself, that should be obvious, but it's true. You have to address the underlying causes of why we've exceeded all these things. It's overshoot. And the only way to back off is going to be, and I'll talk about this in part 4, 5, and 6, is degrowth. That is the only thing we can do. Biomass of wild mammals is in free fall. 17% of wild mammal biomass remains. Anthropogenic stressors on the biosphere. Climate change is only 7%. So exploitation is 37%. Habitat loss and degradation is 44%. And this is pollution. And this might even be more than this now. There's some bad things that we're putting into the environment that are not helpful. Nutrient cycles, When we overfished all the whales, we disrupted this in terms of all the other animals that we went went extinct. Coral reefs, again, they're going to be dead at 2 degrees. This is tropical coral reefs. This is from the SR-15. This is from NASA. This is an explanation of why that's going to happen and why it's nonlinear. The dry mass of human stuff is now exceeds the dry mass of all life on Earth, and it's growing, doubling every 20 years. We can't do that. We can't keep growing the human experience or the economy. It's just impossible. We have to get rid of capitalism, which I'm going to keep reminding everybody, because capitalism can't exist without growth. Earth biosphere is replacing this stuff, is doubling every 20 years. Global mass of produced plastic is greater than the overall mass of all terrestrial and marine mammals combined. Since the first agricultural revolution 12,000 years ago, humanity has halved the mass of plants. And replaced it with a considerably less amount of domesticated crops. All new anthropogenic mass will become waste gradually. In the next 20 years, we will produce as much waste, which goes into landfills, as from the last 110 years together. And most of what we have now has been built since the 60s. And some of it's getting end of life, like nuclear reactors, which were only designed to last 40 years, but they've all got extensions because we haven't figured out what to do, and they've been extended out to 60 years. Climate-related events have increased threefold, probably more than that. High food prices lead to instabilities. These are all instabilities. These are the number of people that died in parentheses. And you can see when we had a spike here in 2008, this was due to the credit crisis, due to our banksters on Wall Street. And this was due to climate change and a massive heat wave that hit Ukraine and Russia. And they couldn't export any wheat, which Russia's the largest exporter of wheat. Ukraine is like the 5th largest. So you take those two off the market and we have a significant problem. Fortunately, we do overproduce. And I get aggravated with people who say, oh, there's so much waste. Oh, we can cut down on the waste and feed everybody. But that waste is our salvation. That's what makes the whole system resilient. If we had no waste, if every grain of wheat and every turnip we grew got eaten, whenever something like this happened, people would die. Lots of people would die. Okay. Oh, and by the way, the index as of March 2022 was 270, so it's up here already. It's off the wall. Okay. The probability that all 4 maize exporting countries, these are the big ones, US, Brazil, Argentina, and Ukraine, have a simultaneous production loss in any given year is today virtually zero. We can lose one, like we probably lost a lot from Ukraine, although they're still producing. But at 2 degrees over any 20-year period, there's an 88% probability that all 4 of them will have a production loss. That's a famine, but it's a manageable disaster. It's not a catastrophe. If we can't do, capitalism can't manage this, but if we had a managed economy, and a managed economy by which I mean a democracy, and because you have to involve people, you can't just rely on a dictatorship or a group of elders or something. It has to be everybody involved and everybody educated. Otherwise, it ain't going to work. And at 2 degrees of warming, which we're definitely heading for, we're going to have one of these every 20 years. But that's, you have a bunch of years, a bunch of good years to in a managed economy to store grain and be ready for your bad year. At 4 degrees of warming, this is going to happen with near certainty once every 3 years. So every 3 years, we're we're just in a serious famine. We're never going to be able to manage that. That's an unmanageable catastrophe. Um, Earth's habitability is at risk. Okay, this is the rate of extinctions. You can see it's 100 times greater. I like this picture. I don't know why. Uh, uh, Okay, so this is the end. What we may have learned in part 3, the climate is in a bistable state. We are close to tipping the climate into 5-degree warmer mid-Miocene climate, but we don't know how close we are. Civilization depends on agriculture. Agriculture depends on a stable climate. We are warming the climate too fast for the biosphere and civilization to adapt. An extinction event, the Holocene extinction, is underway. The planet is not in peril. New battery technology isn't going to save it. Neither is you know, fusion or anything else. The Earth doesn't need saving. The Earth is not in trouble. We are. And so next time we got 3 coming lectures of how we can avoid this problem. And so that's where I have to update this because I'm replacing that with 3 lectures. So how am I doing on time? You got to, oh yeah.
We're at 8, just about 8:30.
Oh, so that was about 45, 50 minutes, maybe.
Yeah.
Oh, that's not so bad. Okay, we can call it there, and because if I expand this to 3 lectures, I'll have plenty of opportunity to add that other material.
Okay, I'll stop the recording.
Thank you.